Swayam Prabha. Digital India. Educated India.
So in the last class, we've analyzed principles of hydrostatics, more generally fluid statics. We have seen how the pressure can vary in various atmospheres, and in this particular lecture, we are going to extend some of the previous analysis of forces acting on submerged surfaces and see how it can lead us to calculate the buoyancy acting on an object. And buoyancy is quite important because, for example, the operation of a submarine depends on how buoyant it is. So we can either push compressed air inside a submarine to make it more buoyant. We can extract the air and displace it by water to make it less buoyant. This is how it can float or rise up or sink down. And buoyancy is important for the operation of atmospheric blimps and balloons as well. So lastly, we will see how stable various objects are which are floating in water. That a small perturbation given to such kinds of objects, whether or not they lead to a restoring of the object to the initial configuration, or whether it diverges from its initial location and takes some other equilibrium position. The question is not to find out the equilibrium position, but to find out whether it will restore back to the original condition. And this is quite important for us to design ships and analyze various floating objects. So buoyancy is the phenomenon where an object which is submerged completely inside a fluid experiences a net thrust against the direction of gravity. So as a result of which there will be two forces. One will be the weight of the object and one will be the buoyancy force. And depending on whether the buoyancy force exceeds the weight of the object or vice versa, the object will float or it will sink. Now, this is an important concept because most of what we see floating on water, for example, like boats, ships, they are all floating because of the buoyancy force. And later on in this particular lecture, we are also going to look at the stability of such objects. The initial ideas of buoyancy were led forward by Archimedes. And we all know it from some earlier classes that what Archimedes said was a body immersed in a fluid experiences a net vertical buoyant force which is equal to the weight of the fluid it displaces. So the important parameter here is the weight of displaced fluid. So in this particular case, this is the volume of the object, and so the weight of the displaced fluid will be the volume of this object multiplied by the density of the liquid. So the density of the liquid is rho. Now if the density of the object is rho 0, so depending on the comparison of rho 0 and rho, we can easily say whether the object will float or whether it will sink. But the important thing is the volume displaced will be equal. So you can take the same volume made of wood or the same volume made of gold. They will displace the same amount of water. However, the buoyancy force acting on the two objects will be, despite the buoyancy force being equal, the net force will be different because gold will have a larger weight given the same volume. So let us try to prove this particular statement that the force due to buoyancy is equal to the weight of the fluid displaced. Let us consider an object as shown and let this object lie submerged in a fluid. Let us consider a certain strip so this is sort of a slice of the object and whatever is the shape into the plane. So for example, if it's a circular object, it is like a slice of the circular object into the plane. Okay, so this is not just a two-dimensional thing, it's going into the plane as well. So now if we consider the surface shown over here and over here, we want to know what is the net upward force acting on this. So the shape of the interface between the solid and the fluid determines the direction of the force because of the pressure. Now arguably we know that the pressure at this particular point is going to be larger than the pressure at this particular point. Let us call the pressure at this point as P1. Let us call the pressure at this point to be P2. This height, let it be Z1, and this height, not height but the depth from the free surface, let it be Z2. So now we can say that the buoyancy force will be integration of P2 minus P1, so times this perimeter, so it will be, let us call it dA perimeter. But now because the buoyancy force is in the vertical direction, this n cap whatever we had must be multiplied by, must be dot product with Ez, that is the unit vector in the z direction, and essentially this is equivalent to writing P2 minus P1 times the projection of these two areas onto the vertical location. And we had done a similar thing in the last class. So if you have a certain ds, so in the last class we had done it for the dam problem. The vertical force is found out by projecting ds onto the x-axis. So this particular thing becomes dA horizontal. This force is acting on the in the z direction. So this would be equal to integral of, so this integration first of all goes over the entire area, so over all the various slices that you can form of the object, over all the different slices. Okay, so now what is P2? So P2 will be rho G Z2 and P1 will be rho G Z1, and this we have to multiply with DAH, that is this projection, which is going to be equal for both the areas because we have chosen a given strip. Let me redraw this slightly more in a large format. So this is the strip that we're talking about, and the projection of this strip is the same for both the top and the bottom. Okay, so this is going to be DAH. So it's essentially integral of rho g z2 minus z1 times DAH. Now z2 minus z1 is sort of this height. So let's call it as delta z at that particular point where DH is evaluated. Okay, so essentially this expression is integral rho g delta z times DAH. So essentially it is this flat perimeter surface multiplied by the height, and this is nothing but the volume. So this is nothing but this particular volume of the slice, the volume of this particular slice, and thus this is rho g times the volume of the object, because you are going to integrate it over the entire area. So you're going to take multiple slices. So each slice you take, you're going to essentially end up with the volume of the entire object, and thus the buoyancy force is equal to the weight of the fluid displaced. Here rho is the density of the fluid, not the density of the object. V is the volume of the entire object, and the volume of the entire object is also going to be the volume of fluid displaced. Now, depending on the force due to buoyancy, there can be a condition where the object is partially floating on top of the water and partially submerged. So in this case, the buoyancy will be due to whatever volume is submerged, that is this volume. The location where the buoyancy acts is called as the center of buoyancy. So if we go back to our previous example, so it was typically the centroid of the displaced volume. It is not necessarily the center of gravity. The reason being, we can have a composite object which contains, say, a heavy object on this side but a lighter object on this side. So because it is containing a heavy object on this side, the center of gravity will be shifted from the center point. So instead of drawing it like a 3D, let me just draw it like a 2D, easier to explain. So let us say this is the heavy part, say something like mild steel. This is the light part, say something like aluminium. The center of gravity will act somewhere over here. But once it is submerged inside a liquid, this is going to be the volume of fluid displaced. It will make no difference what the actual composition of the object is. The point is, this is going to be the volume of the liquid that is displaced, which means that the centroid of this volume will be where the buoyancy acts. It is as if everything is uniform. So this is the center of buoyancy. Now, in static equilibrium, where the object is not having any motion, the center of gravity and the center of buoyancy must coincide, because if they do not coincide, it will result in a net moment. So suppose they don't coincide, suppose the weight is acting something like this and the center of buoyancy is somewhere here. So it is Fb. So if they do not coincide, there is a net moment on the object, causing the object to lose its static equilibrium, and hence it is necessary for them to be collinear under the conditions of static equilibrium. But what about this example that we just said, that it is heavy over here and light over here? Well, eventually the object would experience a moment initially so that it reorients itself in a manner that Fb and W will become collinear. Once it becomes collinear, the object will become static. An object is said to be neutrally buoyant if the force due to buoyancy is exactly balancing its weight. That is, it is experiencing no net force in the direction of gravity. And having neutrally buoyant entities is quite important for flow visualization. So suppose you have a flow in this direction and you want to measure how the flow looks like. So you put a neutrally buoyant particle. Now suppose the flow varies in the z direction. If the particle is neutrally buoyant, it will not have a tendency to rise or sink in the fluid. It will try to maintain same plane, as a result of which we will be able to obtain the true velocity. Suppose the velocity in the lower part of the domain is low. So once the flow begins, if the particle is not neutrally buoyant, the particle will have a tendency to either sink down, where it will encounter lower velocities, or it will have a tendency to rise up, where it will experience possibly higher velocities. So it will not really give us the nature of the flow in the plane that we had injected the particle at. So for having tracer particles to measure flow fields like I just mentioned, we must have particles which are not just neutrally buoyant but also quite small, so that they do not experience appreciable drag. So if a particle experiences drag, its velocity will reduce in comparison to the flow, and thus it will not give us the true indication of the flow field. But more on this when we study viscous flows. Let us take an example. Let's say we have an object which is floating in water, and that the water level is somewhere at this point. It is given that this height is 3 centimeter, this height is 8 centimeter, the body is a cylinder and the diameter is given as 9 centimeter, and it is given that the liquid is water. So if this is the configuration of the body, we must find out what is the weight of the body. So the weight of the body, let's say it is W. So W acts at the center of gravity, which is over here. Now the volume displaced is equal to pi d square by 4 multiplied by the height. So it is going to be, so let us write it in terms of symbols. Let me call this as H submerged. So it will be pi d square by 4 multiplied by H submerged. Now the force due to buoyancy is going to be the volume submerged, let's call it as Vs, times rho of the liquid times G. And it acts at the center of the centroid of this submerged volume, which is going to be somewhere over here. So this is the point of buoyancy, the center of buoyancy B, and this is the centroid C. So the force due to buoyancy is this, and at static equilibrium, W minus W plus Fb is going to be 0, which implies Fb, or rather W, is equal to pi d square by 4 into Hs times rho g. So let us pull out our calculators and crunch in the numbers. So pi by 4 times the diameter is 0.9 square times the height, which is so it's 9 centimeter, 0.09 square times 0.08 times rho, which is 1000, and g, which is 9.81, and it comes out to be 4.99 Newton, or essentially it is 5 Newton. So the weight of the block is 5 Newton, and that causes it to sink to this particular level. It does not cause it to sink completely. Let's try to analyze. I mean, we found out the answer. Okay, we found out the answer, but let's try to just read between the lines of this particular question. This particular weight causes the body to not sink completely. And if we were to be given that a block exists of this particular weight, find out the gap remaining. Our first task would be to parameterize height of the body. So the reverse calculation, if we were to be given that the weight of the body is 5, we would say the weight of the body plus the force due to buoyancy would be 0. We can first assume that the entire body is submerged. So if we assume that the entire body is submerged, then we would end up with a buoyancy force which is equal to the entire volume of the body times density times rho. So it would be rho g pi d square by 4 multiplied by the height of the body, which would be 11 centimeter, which is 0.11. So let us just quickly find out what this buoyancy would be. So 0.09 square times 0.11 times density times 9.81, and it comes out to be equal to 6.86 Newton. So if we assume that the entire body is submerged, then we end up with a buoyancy force of 6.86 Newton, which exceeds the weight of the object. If the buoyancy force exceeds the weight of the object, it means that there must be a lower volume which is submerged to reduce the buoyancy force to make it equal to the weight. So then we would parameterize. Let the height above water be small h. In that case, we would have written the volume submerged, that is, uh, directly we can write the density times gravity times the volume submerged, which would be pi d square by 4 times the volume submerged in this case would be 11 centimeter minus h. So in terms of meters, it would be 0.11 minus h, and this would be balanced exactly by the weight. and this would naturally give us a h of 3 centimeter. This is the way to go about it. Let us consider one more problem. The problem is as follows. We have a long piece of wood. It is given that the cross-section area of the wood is 5 centimeter by 5 centimeter square, and that the length of the wood is 2.2 meter. So the question is, how much lead should be attached to the bottom of the wood so that this particular entity is floating with 30 centimeter out of the water. So when it is floating, this distance is 30 centimeter. So this is the problem. Let us see how to address the problem. Now we know that if 30 centimeter is above, 1.9 meter of the wood is underwater. So let us write down the buoyancy force acting on the entire system. So this particular thing is lead. So the buoyancy force will be the volume of lead multiplied by rho of water times G plus volume of wood times rho of water times G. Whereas the total weight of the system is volume of lead times density of lead times G plus volume of wood times the density of wood times G. It is given that the specific gravity of wood is 0.65, that is, it is 0.65 times the density of water, whereas the specific gravity of lead is 11.4, meaning it is 11.4 times more denser. It is 11.4 times denser than water. So now if we equate these two, okay, so the volume of wood submerged, okay, the buoyancy force will be because of the volume of wood submerged. Now we know that the volume of lead would be volume of lead because everything is submerged. This would be the total volume of the wood. So volume of lead times 11, not 11. Let us write down the left hand side first. It would be the volume of lead multiplied by the density of water times G plus the volume of wood submerged, that is the area of wood multiplied by 1.9 meter times density of water times G, and on the right hand side we will write down the weight of the system, which is the volume of lead times rho of lead times G plus volume of wood total, which is the area of wood multiplied by 2.2 times rho of wood times G. This 2.2 is the total height of the wood. Now G cancels out from all the sides, and rho water can be divided. Okay, so this is rho wood. Just to avoid the confusion between water and wood. Okay, let's divide everything by rho water. So volume of lead plus area of wood times 1.9 is going to be equal to volume of lead times rho of lead upon rho of water plus area of wood times 2.2 times rho of wood divided by rho of water. This is VL times 11.6 plus AW into 2.2 into rho wood upon rho water is 0.65. So VL times 11.6 minus 1 is equal to AW times 1.9 minus 2.2 times 0.65. I have just rearranged the terms in the expression, which implies that VL, so the area is 5 centimeter cross 5 centimeters, so it's 0.05 square upon 10.6 times 1.9 minus 2.2 times 0.65. So if we crunch in the numbers, we obtain the volume of lead as 1.1 into 10 to the power minus 4 meter cube. Correspondingly, the weight of lead is the volume of lead, which is 1.1 10 to the power minus 4 times the density of lead, which is 11.4 times the density of water, times G. And this comes out to be 12.4 Newton. So the weight of lead that needs to be attached at the end of the rod to make it float 30 centimeters from the surface of the water is equal to 12.4 Newton. Let us now consider the stability of floating bodies. We know that the force due to buoyancy acts vertically upwards, and the magnitude of this force is equal to the volume of water displaced or the liquid displaced times gravity times the density of the liquid. So if the force due to buoyancy is larger than the weight of the object, then the object will float and it will achieve a configuration where it is partly submerged in water and partly above water. So in this case, the buoyancy is because of the submerged volume that lies below the water line. So this particular line is called as the water line. That is the perimeter that you see, and whatever is submerged below is responsible for the force due to buoyancy acting at the center of buoyancy, that is the centroid of the volume, while the weight acts as it is. Now under static equilibrium, we know that these 2 points will be collinear, meaning there will be no net torque. If they are not collinear, there will be a net moment and the body will rotate and it will reorient itself until it acquires a stable configuration. But what is a stable configuration? Consider balancing a pencil on one of its ends. Now, classical mechanics, or rather in this case, dynamics tells us that this pencil, when it is perfectly oriented at 90 degrees, it will be at static equilibrium. But common experience tells us that it is extremely difficult to do, point number one, and even if you are able to do this kind of balance, any small disturbance will cause it to fall down. And it will fall down to a position something like this. Now, this is the stable equilibrium position. And This is called as the unstable equilibrium position. Both are equilibrium positions, but one of it is unstable while the other is stable. Now, a similar thing happens for floating objects. Let us consider a certain floating object as shown. This particular object, marked by this blue color, is floating in water in such a way that part of it is submerged underwater below this particular line and part of it is above water. If we consider this to be an egg-shaped object, the top view, so this is the side view, the top view would of this particular water line would simply be a circle. Below the circle is the submerged object, above the circle, meaning out of the plane towards us, is the object facing water, facing us in the air. Away from us into the plane would be the submerged part. So now let us draw the center of gravity of this object. Say it is somewhere over here. Let us call it as G, center of mass, and it acts something like this. Now the center of buoyancy will be calculated from this particular volume. So it will remain somewhere over here. For argument's sake, let us say that we tilt this object slightly. To a position something like this. So what happens when you induce this kind of a tilt? Let me draw the original axis. It is going to be something like this, and this is the angle that you have tilted it by. So now the volume that is submerged changes and it has a net bias. But so if we say that the center of buoyancy is at this point, let me call this as B, and the weight of the object acts somewhere over here. So in order to show this clearly, let us exaggerate the diagram a bit. Let me say that the center of mass acts somewhere over here. So the center of buoyancy, the force acting at the center of buoyancy is the buoyancy force, and at point G, the weight W will act. So upon inducing a counterclockwise tilt, what happens? Let us look at the net moment. The moment is going to be, let us take the moment about point G. So about point G, the net moment will be this moment arm multiplied by the force. Let me call this as delta. So the net moment will be Fb times delta, but the direction of this moment is clockwise. So it will be minus Fb times d. So this minus is due to the sign convention. So when you tilt, or rather when you sort of try to rotate the object about this axis, there is a net moment in the clockwise direction. So the anti-clockwise tilt leads to a clockwise moment. This means that this moment will try to restore the original value of theta, that was 0 degree. So it is a restoring moment. So in such a case, it is like taking a pendulum displacing it by an angle theta, and seeing how what happens to this pendulum. So it will try to come back. So this is the case where the force is restoring in nature. Let us take another illustrative example. Let us say, for argument's sake, that the force due to its own weight, it acts through this. So let's call it G. This point is G, but the center of buoyancy is over here. So let me call this B, and the force is FB. So again, even in this case, what we have done is we've tilted it about this particular axis in the counterclockwise direction. So the tilt is counterclockwise or anticlockwise, whatever you want to call it. Let us take the moment about point G. It will be equal to this force FB multiplied by the moment arm. So it will be moment equal to FB times delta. But now look, the moment is in this direction, that is, it is also in the counterclockwise direction, so there will be a positive sign. So given that the tilt is counterclockwise, the moment is also counterclockwise. So the force is not a restoring force. So this, rather the moment is not restoring the original position. I mean, forget about the original position, it's not a restoring. So once you tilt it by some small angle, it will keep on going because the moment is also trying to increase this particular theta. In this particular case, when we increased theta in this direction, the moment tries to bring it back in this direction. However, in this particular case, the moment tries to take it further and it tries to remove it from the original equilibrium position to something else. So this is the case when you take a pencil and it goes to a new equilibrium position. It falls down. Or if you want to make an analogy with the pendulum, it is something like an inverted pendulum. So you take a rigid rod and you put a bob on top of it. So obviously this is also an equilibrium position, but the moment you push the bob to one side, it will suddenly go around and take this position because this is the equilibrium position, stable equilibrium position. So this is the unstable equilibrium position about this pivot point, and this is going to be the stable equilibrium position. So despite us having equilibrium positions, whether or not they are stable or unstable is decided by whether or not the force or the moment is restoring or not. So restoring means it takes it back to its original configuration. So a small disturbance, if it goes back, then it is a restoring force. If it keeps going in that direction and forgets about its initial position, then it is not a restoring force. Before going into the mathematical details of whether a certain configuration is in equilibrium or not, let us first define certain terms. So we're going to look at what a metacenter is. It is basically the intersection of the line of symmetry with a vertical line passing through the point of buoyancy. So let us say that this point is G, that is the center of gravity, center of mass, and the point of buoyancy is somewhere over here. So let us draw a a vertical line through point B. It intersects this line of symmetry over here, and so this point becomes M, the metacenter. This is point B. So in this case, the tilt is anti-clockwise. The restoring moment, so this is the force and this is the moment arm. So the restoring force, the restoring moment is clockwise, and so when M lies above G, right, we have a stable configuration. That is, when we disturb the equilibrium position, it tries to restore it back to its original configuration. Let us look at the other case where you have G over here, but say the point B is over here. So we draw a vertical line through B and it intersects the line of symmetry over here, and this is called as the metacenter. Now we have disturbed it in the same anti-clockwise direction, but now the restoring force is, so this is going to be the direction of the force acting at point B. So this is going to be the direction of FB, and FB is trying to rotate it like this. So the restoring moment direction, actually it's not the restoring moment, the moment direction is also anti-clockwise. So the tilt is anti-clockwise and the moment is also anti-clockwise, so it's not a restoring moment, meaning when M lies below G, the configuration is an unstable configuration, meaning that a small disturbance causes the force of buoyancy to act in such a way that it causes a further increment in the disturbance. It does not restore it back to the original configuration. Let us now consider the stability of such floating objects. It is very important from the point of view of naval architecture to determine a priori whether a given hull shape, so the hull is the cross-section shape of the ship if you want to sort of make a rough definition, but whether or not that hull shape is stable to oscillations is a very important question. And let us see what the mathematical theory is behind that. Let us first of all let us appreciate that, I mean, most of the engineered objects will be symmetric, or at least the hull is symmetric, even if the weight distribution is not symmetric. Usually, the weight distribution is also kept done eventually in such a way that it's symmetric. But for this simple example, let us say that we have a hull in the shape of this white contour, and this is the cross section area. And so the water line is this. So this is the water line. In the top view, this water line, say it's going to look something like this. And it's pointed towards the end because the ship usually has a pointed end, right? So this is that pointed end will whatever the intersection of that contour with water will be is this shape. But we can have a barge. So barges are big cargo carrying ships. So they are just like square boxes. So nevertheless, they can have a square cross section, in which case the water line from the top view would look something like this. It would be much simpler. But regardless of that, whatever theory we're going to do is not going to depend much upon that particular shape. It's going to depend on something which is like a function of that shape, but not that shape per se. That equation will be required. So now let us consider this particular object, and this is the center of mass, and the center of buoyancy will be this, and it will be calculated, I again repeat, with this particular volume in mind. If I call this A, B, C, D, that A, B, C, D volume will give us point B, that is the buoyancy. So this is FB and this is going to be W. Now typically when there is a small disturbance in the ship, so everything's gonna have a net tilt. Okay, so suppose you tilt it, suppose there is some disturbance in the water because of which it tilts in this direction. So then the question is, what happens because of that particular tilt? Let me draw the tilted object. So when the disturbance causes a tilt, in this case the tilt is clockwise, and usually we analyze everything as a small disturbance. Because the small disturbance gives us the behavior of the system when there is a slight perturbation from the equilibrium position. So this small disturbance is to understand the behavior of the system under what we say as a perturbation. And this kind of response is called as a linear response. So just for your information, it's called as a linear response. Because even in the case of pendulums, anyone who has done this analysis, and I hope everyone has done this, when you do this, so the restoring force is like a function of sine theta, but when you have small disturbances, sine theta is tantamount to theta, and so it becomes like a linear response, because sine theta is a nonlinear function and theta is obviously a linear function. So what is the sort of physics that is involved? So about this point, when you tilt it, this extra volume is submerged. So this is the new submerged volume. I mean the added submerged volume. So original submerged volume, let me call it as small a origin B. So this point is B, C, D. So initial submerged volume is A, O, B, C, D, A, that particular perimeter, and into the plane whatever depth we have. This is the area multiplied by width into the plane. That gives us the volume. But now, because of the tilting, this hatched volume is extra. So let me call this as B prime. Let me call this particular point as A prime. So after tilt, added submerged volume, that particular volume is going to be BO B prime, and removed submerged volume, meaning it is no longer submerged. So AOA prime. So AOA prime is no longer submerged, and this means that we have gained some buoyancy over here and we have lost some buoyancy over here. And because the new volume is going to be A prime O B C D, it's going to be this particular hatched area. And since you have gained some amount of volume over here and lost something, the center of buoyancy will shift to a slightly different value. The buoyancy will shift in this direction. Okay, so that is the physical consequence. The buoyancy will shift over here, and that shift in the point of buoyancy is what we really want to analyze, whether that shift in the point of buoyancy leads to some kind of restoring moment or it does not lead to a restoring moment. So in this video, we've looked at the analysis of buoyancy, which was an extension of forces acting on submerged bodies. We've looked at how we can find out the force due to buoyancy and the location at which it acts. We've seen how we can find out how much volume above the surface of the water we have for various bodies and how it can be altered by addition of additional weights. Then we moved on to analysis of stability and how the metacenter plays an important role in assessing whether a given object which is floating on the surface of water is going to be stable to arbitrary perturbations or not. And it was seen that if the metacenter lies above the center of mass, then we have stable equilibrium, meaning a small perturbation gives rise to a restoring moment in such a way that the object restores or it comes back to its original configuration. If the metacenter does not lie above the center of gravity, the center of mass in this case, it will be that a small perturbation given to the object will amplify. It will not allow the object to come back to its original position, but rather it will diverge away from the position and go to some other equilibrium configuration. And we have seen the analogy with the balancing of a pencil or even a pendulum clock. So with this, we end this particular video, and I will see you next time. Until then, it's goodbye from me. Bye.